Hello, everyone, and thank you for joining us today. My name is J.C. Hernandez from NASA Johnson Space Center, and I will be your moderator for this webinar on the Coil-On-Plug exciter for rocket engine ignition. As part of my role at NASA Johnson Space Center and NASA Technology Transfer, I work with NASA scientists who develop new technology that may have applications outside the aerospace industry. Our presenter today is Bill Studak from NASA Johnson Space Center. Mr. Studak is a senior design, analysis, build, and test engineer with 33 years of experience in propulsion and fluid components, systems, and flight hardware. He's designed, built, and tested numerous propulsion components, thrusters, and systems using cold gas, inert liquids, and various combustible propellants. He has worked on propulsion systems for the space station, the space shuttle, Orion, lunar, and Mars landers and ascent vehicles. He has led numerous developmental efforts, including liquefaction and storage of rocket propellants created from lunar and Martian resources. He designed the propulsion system from the jetpack used by astronauts during spacewalks. Mr. Studak earned his BS degree in mechanical engineering from the University of Texas at Austin. Go Longhorns. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box and we will answer them during the Q&A session at the end. At this point, I'm going to turn it over to you, Bill.
Hi, everybody. I'm happy to see everyone here today. I see I've got a crowd of 40 and growing. I hope I've got something interesting for you all. The pitch I've got today is about 1/3 background, talking in general on the problem of ignition of rocket engines, and more particularly the reignition or frequent ignition of rocket engines, especially as applied to attitude control systems, and especially as applied to cryogenic systems. Then I've got about 1/3 that talks about the particular device that we invented here and tested. And then about 1/3 of it will be the testing to date and some applications and our success at this point and our future work. So with that, let's go ahead and start the next page, please. The background and the motivation kind of tie into each other. The operational overview and the benefits are basically our attempt to improve the state of the art. And then we're going to talk a little bit about some specific examples that we've done here and the improvements that we're ready to make based on where we're at right now and hope to be in the near future. Chart, please. So for those of you in the business who are familiar with igniting large rocket engines, some of this material will be very familiar. There are other folks who are less familiar. And really the application is dialed into the particular idea of lighting a small torch. So broadly speaking, you've got to have some kind of a spark or ignition source. And there are plenty of ways to do that, especially as applied to large engines. As the engines get small, and I'm really talking about reaction control engines here, those ignition systems become large compared to the thruster, and that's a problem. So, the typical answer is we flow the propellant through the injector, we can throttle it as required, and we typically would use a small torch, which would be, as shown in this particular example, you've got a small torch that provides the initial flame source. And then in this particular picture, you can see there's a little cluster of 7 main injectors that surround the torch. This is a rocket engine without chamber, obviously. This is a ground development unit, obviously. And that ignition torch in this picture, and I chose this on purpose so that you could see a good example of the separate elements that are required just for the igniter assembly. In this case, you've got 2 gas feed lines, you've got a clearly automotive inspired high voltage connector spark plug, a small mixing chamber, and then of course the blue-white flame coming out roughly in the center of the chamber, a little bit transverse to the chamber diameter. So that's kind of sets the stage for a classic spark ignition, torch augmented ignition system. Chart, please. So I'm going to talk a little bit more about an aerospace version of that spark ignition system. And when we first started this effort, and I'm looking back in around the early 2000 timeframe, as we started looking at non-toxic propellants, broadly speaking, and we quickly found that a very common use in the full-size rocket engines, and I'm looking at boosters and upper stages right now, were aircraft derived, and thus there would be a control electronics box that would be in its own enclosure. It may or may not have its own power supply. It has some kind of a timing circuit, some kind of a high voltage conversion circuit, some kind of cable that is heavy, relatively bulky, has large connectors because it is a high voltage cable, and we're talking anywhere from 10 to 30,000 volts here. And of course, the connectors themselves tend to be large and bulky in order to provide appropriate isolation for that high voltage spark. And then, of course, there's a spark plug of some sort that is actually the electrode that goes inside the igniter torch mixing chamber or torch assembly, depending on the exact configuration. And so this is sort of the starting point, for many systems, not all. The space shuttle had a fairly compact version of this, but this was actually a starting point for many development engines back in the 2000s. So this is sort of freeze frame this, and then we'll move forward now and talk about what we'd prefer to have. Chart, please. Oh, so some issues with these traditional igniters to clue you in on some of the problems we had. So conventional spark plugs, aircraft and turbine engines have ceramics that are exposed to the incoming propellant flow, which is maybe okay for most propellants until you try to flow cryogenic propellants over them. Not surprisingly, ceramics don't like sudden thermal shocks. Now, and you also have very high temperatures in close proximity, so exacerbating the thermal shock problem, and cracking the ceramic was a very common problem. The high voltage cables themselves are problematic. They have often, they start off insulating very well, but then as you go into a vacuum over time, they may actually permeate gas that has permeated in will start leaving you with insulation breakdown and corona effect, right? And so you can have an intermittent cable that works sometimes and not other times, or it works for a while and then it stops for a while, and it starts working again. As you can imagine, very frustrating situation. The connectors themselves are prone to damage. That is, you can have continuity problems with them, and they're large and heavy inherently because they're trying to insulate against very high voltages and also be disconnectable and reconnectable. The control electronics themselves, if they're mounted on the engine or nearby, in any case, they're subjected to very high loads, and these electronics can be built to withstand such things, and we have successfully, but it does inherently mean that you're going to have a larger enclosure with heavier duty components that are derated to a higher level. And they're still going to be subjected to high, perhaps shock loading, environmental swings, vibration loading, hot and cold temperatures. So these are all kind of the downside of the more or less traditional approach, or what was the traditional approach. Chart, please. So here we've created an illustration here. Now, this illustration isn't meant to be all encompassing in the sense that this is the only way or the way a lot of people do it, but it is meant to illustrate the complexity inherent in having a gas supply required for your igniter torch, along with the electronics that I just spoke about. So sometimes a large engine, you'll vaporize the low pressure liquid so that you can inject it as a gas, or maybe you have a separate gas feed system. Sometimes you try to inject liquid, but then you need a lot more energy. So you're fighting yourself and trying to get good conditions for ignition. In any case, these separate systems, that is the gas supply or a vaporizer, and the electronics, the cable and so forth, all these things together add bulk and complexity, inherently reducing reliability. And not that this is the universal answer, but it does illustrate the point. And here's where it gets really complicated. When we started working cryogenic RCS in the mid-2000s, we quickly recognized that you simply can't have these kinds of separate systems clustered together for maneuvering systems that require a lot of jets. Chart, please. So to illustrate my point of the complexity, here this graphic is meant to illustrate, if I take those boxes and cables and so forth that I showed you earlier and put 4 of them together in a fairly typical cluster of 4 thrusters for maneuvering systems, then you can see that 90% of what you're looking at is not the thruster. And that's inherently a problem. Main engines can maybe accommodate the volume required by these separate components. But once you start looking at very small thrusters, then the electronics and the cables and so forth are bigger than the thruster you're trying to ignite. So clearly there's a mismatch there. And setting that aside, the complexity, there's another side, which is the common commodity argument, which says that it would be nice, it would be preferred if all your thrusters could use the same propellant that the main engine is using. So if you could use that, at least it simplifies your fluid system. But clearly packaging 30 or 40 of these small boxes, the cables and the connectors and all that stuff, is really not a very mass efficient solution. So this sets the stage for why we went down the road we went down in order to, build a better mousetrap. Next chart, please. Okay, so the picture really says it all, and this is roughly to scale. We needed to take what you see on the left and turn it into what you see on the right. Now, that's not a completely fair comparison, because we would and do in this case take the low voltage electronics and have them remote, and on the right hand side, the improved coil-on-plug exciter assembly does not have the low voltage electronics. It has only the high voltage conversion coil. But here's what we've accomplished. We've gotten rid of that high voltage cable completely. The exciter assembly is now much closer in size to the small thrusters we're trying to work with. And because we've taken the sensitive low temperature environment and separated the more sensitive electronics away from that more challenging environment, those avionics are going to be much happier. Meanwhile, at the thruster end, those parts, the coil especially, is really pretty impervious to things like shock and vibration and so forth. It really doesn't care. It's got no moving parts. And so this gives you a snapshot of what we started with and where we ended. And so now we can look at the next page. And we're going to look a little bit more closely at it. So here what we've done is we've got nothing but a low voltage connector. So that cable is relatively lightweight and the connector itself is relatively small. The coil-on-plug housing is quite compact and still getting us upwards of 20,000 volts at spark tip. Because it's integral to the electrode, there is no cable, and we can basically screw this assembly directly into the top of the thruster as the igniter assembly, as the exciter. So by combining these elements into one integrated package, we've eliminated the cable. We do have cryo-rated potting in there, an epoxy that we can install, and we've virtually eliminated the exposure to cryogens of the ceramics in this particular model. And as I said, the low voltage circuits are relocated back to the common avionics compartment where all the other avionics live. And so we've actually put them where they'd prefer to be anyway. Oh, excuse me. Chart, please. So here we see that earlier graphic now reduced significantly to the graphic on the right. And so this shows those coil-on plugs on those small thrusters. And I mean, you know, the difference in mass and volume is self-evident, I think. You know, those coils are very durable. They're very tolerant of environmental extremes. Relocating the low voltage electronics away from the cryogenics improves their reliability. And you can further simplify the avionics because the drivers for these coils, they can be co-located on a single driver board. And so now you're treating these coils much more like you would treat valve driver boards, for instance, wherein you can have 16 or 32 channels on a single board because the amount of power on the low voltage side is actually fairly modest. We've gone to low voltage connectors, and secondary structure can even be reduced, as well as the packaging can be improved, moving you perhaps closer to the outer mold line, for example. So this is where we're trying to get to, and in fact, where we arrived, and I'll show you some pictures here soon. Chart, please. So to drive the point home, you know, it's not just about RCS. Advantages to main engines are also significant. Essentially the same coil-on-plug exciter assembly can be used on a main engine in much the same way. You can get rid of a separate gas feed and go with straight cryogenic feed. You can move your sensitive electronics away. A lot of main engines have a main engine avionics box attached nearby, so your exciter driver circuit, the low voltage side, can be co-located with the rest of your engine controls. And again, your secondary structure could be reduced, assuming that you had a gas supply system or something similar. So we think it has significant benefit in both fields, perhaps more so on the RCS application. And so this is the setup and the principal background and reason for the improvements. Chart, please. So to dive into the assembly itself now, along the way, we were working on several different thrusters and engine applications. And so as part of development, we built these to have interchangeable or at least adjustable, in some sense, electrodes. So we could build a core assembly and attach an electrode as required for different thrusters or engines as required. And we can modify the housing, make it a little shorter, longer. We can change the threads and so forth. You know, the smaller connectors, means that it's a much easier device to integrate because you don't need as much volume now just for the connector and access of the connector as you used to. And so here's a couple of different versions that we built. One with does not have its electrode tip installed. The other one does. You can see there's slightly different housings as we iterated through our development cycle and came up with variations on the theme that would support different applications. Chart, please. So now we're finally starting to get into some of the design details. So here you see the igniter and cross section. This is one that we happen to build for a LOX liquid methane thruster. And, the seal geometry can be modified to better accommodate, for example, higher pressures or lower temperatures, and could be further optimized. At this point, we've got it working well. And you can see here that the ceramic exposure to cryogenics is very limited to that sort of T-shaped or top hat shape toward the lower right. And then the insulator has its own seals, principally for pressure, but with all the soft goods in there, it also provides electrical isolation. And then the coil is both connected directly to the electrode, so there's no intervening cable or connectors, and it's potted both for mechanical strength as well as insulation capability. Chart, please. Thank you. Yes. So here you see the same exciter assembly in exploded view, and you can see a little more clearly the lower insulator has very little exposure, so the thermal induced stresses are very small, much reduced. The seals and the upper insulator, the electrode core that eventually attaches directly to the coil-on-plug. And then, of course, the interchangeable tip is not shown here, but you can see the threaded portion of the electrode core that would accommodate different tips. Chart, please. So this is one of several thrusters that we installed this exciter in for extensive testing, principally with LOX methane. And it shows one of the many electrode tip styles, the classic mushroom shape, providing a spark gap with methane injection immediately downstream. And here you can see that in stark contrast to the earlier and some alternate high voltage assemblies. Here, the whole exciter assembly, at least it's about the same size as the thruster itself. And in principle, the same basic configuration can be used on a main engine. Chart, please. So I'm actually headed into the wrap up. I've moved pretty quickly through all this. In terms of applications and benefits, pretty much any application that needs this kind of compact assembly, especially if you're working with cryogenics, where conventional spark plugs, that is the ceramic within them especially, is prone to cracking. We're improving the reliability, not just on the ceramic insulators, but also the elimination of the cables and connectors, getting the low voltage electronics away from the harsh environments, being able to modify this quite rapidly to fit different applications. For main engines, of course, it is a bit smaller and provides that kind of improvement. Thrusters, when you have a lot of thrusters, is especially where you get the payoff because there can be so many of them. And in eliminating all sensitive electronics, you both make the package smaller as well as put those avionics that are sensitive off in a place where, well, they're co-located with the other avionics. So you don't have to have a special box just for this. Chart, please. So to some experience that we've had with these exciters. Pardon me, my allergies are really hitting me hard this month. Some of you may be familiar with the Morpheus project. That was the genesis for a lot of this work here at JSC. We did take that system up to Plumbrook and had some trouble igniting the thrusters once we were cold soaked. Since then, however, we have improved our test stand, and we've now demonstrated that we can light the thrusters down to 150 Kelvin at our normal operating pressures. And we've been working on designs and capability for higher pressure and colder temperature consistent with hydrogen applications. And there are other seal designs that we've sketched up, and some of them we've prototyped to further extend our capabilities to higher pressures and lower temperatures. Chart, please. So here you see on the left the Morpheus core vehicle as installed at Plumbrook, and this is where the main engine lit successfully, but the thrusters were challenged, and we've since overcome that challenge with our new coil-on-plug exciter assembly. And in the upper right, you see basically an IR image of our RCS thruster firing there off to the side. And below, you can see a setup there at Plumbrook for one of our successful firings, where you can see the thruster is working, but that was prior to its cold soak. So we had to come back here and work on the cold soak problem a bit more. And the coil-on-plug exciter assembly that I talked about here today has successfully passed the cold start conditions that were unsuccessful during the Plumbrook test. So we feel like we've overcome that challenge, and we're ready to go to even colder temperatures. And I think that was my last chart. Yes.
Well, thank you, Bill. That was super informative. I personally have always been interested in propulsion. I know that at least in space, there's certainly a trend to move away from the toxic hypergolic directional thrusters, and really like your work and working with methane and liquid oxygen. So really excited about this and excited about all its different applications as well. Not just directional thrusters, but main engines too. And especially in considering your background and investing research into landers on Mars, for instance, where we I guess intend in the future to run escape vehicles on liquid oxygen and liquid methane. I can see how this technology also has obviously a great fit there. But also, and it seems to be as I'm looking into the chat and questions, that we have some, there might be some terrestrial applications as well. So real quick, I'm going to briefly speak to the slide that is in front of you. So to access technologies like this through the NASA Technology Transfer Program, you can search for them in NASA's Technology Transfer Portal at technology.nasa.gov. On each technology page, you will find buttons to send us questions or apply for a license, and our team will get back to you promptly with more information. Next slide, please. So here you'll find a direct link to the Coil-On-Plug exciter for rocket engine ignition. And this particular direct link will take you to a document on our portal, which will describe the technology and also provide these links that we speak of that are on this slide as well. So with that being said, and excited for your replies and glad to see input in the chat box. We want to thank you everyone that's submitted questions so far. So please feel free to continue submitting your questions by typing them into the chat box. If we don't get to all the questions today, then we will follow up with you by email afterwards. Okie doke. So let's see here. I'm going to, Bill, I'm going to switch over here and I'm going to read you some questions from the audience. Can you elaborate on where the high voltage versus low voltage gets created in this system?
So typical of inductive coil ignition. There's a low voltage coil that is high current, low turns, low voltage, surrounded by a high turn coil that is low amps, high voltage. That is the conversion is in that coil on the plug. That black cylindrical object, most often seen on the left-hand side of the assembly, is in fact the high voltage conversion coil. That is, it has the low voltage coil surrounded by the high voltage coil, wherein typically a square wave control signal at low voltage is injected, and at every instance where the square wave is turned off, the magnetic field collapses and essentially squirts out through the high voltage coil across the spark plug gap in an effort to, you could argue in an effort to maintain the direction of the magnetic field, or in order to conserve energy, either way. So the voltage conversion is in fact inductive in this case, and it's a conventional kind of a transformer, basically. And that's what does the conversion.
Gotcha. And Bill, is this similar to a Coil-On-Plug ignition system for internal combustion engines and automotive application?
Absolutely. In fact, it's derived from exactly that concept. The Coil-On-Plug, in general, that expression or that terminology has been around for quite a while. What we've done is basically have some custom coils made that are cold temperature tolerant, combining them with our integral electrode and the potting that provides a structural attachment. So it's the combination of those things together. The Coil-On-Plug concept, of course, is not terribly new. It's been around for a while, and is definitely part of the inspiration for what you see here.
Ah, gotcha. Thank you for that. Next question reads, can this technology be adapted or possibly scaled for non-space applications, where there might be a more dynamic environment in terms of, temperature or I guess, air temperature or fuel temperature, such as maybe, high altitude, aircraft engines, possibly even in the scramjet field. in lower altitude, maybe industrial burners. Do you see any possible applications for this technology in just those areas that we mentioned?
I don't see any limitation inherent with the design of the of the fundamental invention here.
Mm,
The ability of it to run at vacuum or in one atmosphere, it's really indifferent to back pressure, and it's really indifferent to most reasonable temperatures. There are currently some soft goods in it that might set an upper temperature limit. It's true. We were working the cryogenic end of the spectrum principally, but I can't think of any reason it cannot be applied to any combustion system that has some kind of oxidizer and fuel combination that could benefit from having a spark and a compact spark exciter
mm.
nearby.
Oh, fantastic, fantastic. Um, What kind of maintenance or maybe life expectancy can industry partners expect from these modified igniters when integrated into their propulsion systems? Looking at the diagrams, it seems to be that there's certain components, seem to be somewhat modular. That it can be taken apart, and modified for different applications, like you had mentioned. Um, I'm assuming that any maintenance that needs to be done is appears to be relatively easy.
Yeah, I think, to my mind at least, maintenance would come down to what principally is what is the fuel you're using, because fuels that would tend to soot would obviously interfere with spark path. And so that says much more about the choice of fuel and application. And, I really can't speculate on how that might play out. It is fundamentally just a spark plug, in one sense. It happens to have some particular attributes that we were after for our applications, but it is ultimately a variation on a standard turbine engine igniter assembly. I would expect, therefore, you might have similar maintenance requirements that you would see in a turbine engine or other similar industrial type application. But it doesn't have any particular inherent limitations. Uh, the coil is essentially indefinite life. We've done thousands of ignitions, and because we tend to run it with LOX methane, which burns very cleanly, we don't ever clean it. It just doesn't come up. Uh, but I think that says more about methane than it does about other applications. Hopefully that helps.
Sure, sure. Okay, moving on to the next question. Um, what is the spark energy that a thruster system requires for ignition? And there are obviously different types of architectures and different types of fuels, but let's say in a LOX, methane environment, uh, what sort of energy is needed for ignition?
Yeah, so that's a tricky question. And it's really hard to answer because it's very particular to the operating conditions of interest. But I can speak in general terms that broadly speaking, for oxygen hydrogen ignition, excuse me, um, you need something on the order of 5 to 15 millijoules, depending on the exact state of the fuel and oxygen. That is exactly how cold they are. So pretty easily achieved by really almost any spark. That's part of the danger behind hydrogen, right? Is it's so easily ignited.
Right.
Moving up to say a methane, you're up in the tens of millijoules, depending on your precise conditions. Somewhere north of 40 millijoules is usually considered reliable, and anything north of say 60 or 70 millijoules per spark is highly reliable. And we designed around 75 millijoules as a sort of nominal uh, uh, energy made available. The trick with spark plugs, of course, is in general, you can trade energy, current, spark plug gap, and voltage against each other. So you can have more millijoules in less time, but maybe that's too fast. You can't carry the spark downstream.
Sure.
Or you can have a lower energy spark that's more of an arc that is more persistent, that perhaps for a given design will be more applicable. So the design of a combustor or an igniter as installed in a larger application is quickly becomes a kind of system design. That is, a single coil can provide you different kinds of energies, different levels of energy and different durations of spark, and you can trade these things off against each other. So the core device can be operated across a wide range of outcomes depending on exactly the application that you have, which is kind of a squishy answer, but that's the reality of it, is that this this conservation of energy is always there, but how you deliver it is somewhat negotiable by spark plug, by pressure, by voltage, by frequency, by duration. You know, there's a lot of knobs that can be turned, all while holding the energy per spark constant. It's a really interesting dynamic interplay between all these variables. And so an application requires some effort, I think, to optimize it to give you the kind of margin most people would like to see in their ignition system.
Excellent. Okay, moving on to the next question. Roughly, there were a couple of different iterations that were pictured in the presentation, but what's the product's mass roughly in its current form? And have you done any mechanical shock testing?
We have not done shock testing, and excuse me, the current mass, sorry, the current mass, I would guess is on the order of, trying to do the math in my head, about 8 ounces, give or take, maybe 10.
Okay. All right. Thank you.
So what is that? Maybe 200, 250 grams, something like that.
Okay. All right. Thank you for that. Let's see here. Are the spark or current voltages limited? Do you use a time constant or an energy rated spark?
I guess I would express it. Excuse me. I guess I would express it as a duty cycle on the driving square wave, which has to be long enough to saturate the coil, beyond which you're kind of wasting time. And so a given coil, such as this particular one, does indeed have a time constant. Your spark frequency typically is on the order of, 100 hertz, give or take, is a common setting, although it's kind of variable. And the discharge is on the order of the same time frame as the charging cycle.
Oh,
Excuse me.
oh,
And so we don't really. I mean, there is a time constant involved in the charging cycle, and you're trading off your duty cycle and your pulse width against the total energy you're putting into the coil, and how many sparks do you want to deliver after you've achieved ignition. It's possible to just heat the coil up and well beyond the point after which you should have had ignition. So I'm not sure if I answered the question exactly. It's hard to tell.
Okay. No. At least, I'm reading the question, of course, from the chat room, but it seems that you provided a very comprehensive answer. So thank you for that, Bill. There's one of the things that seems to make this technology great is all the variability. And yeah, you're absolutely right. There are so many uh, there are so many components in different settings and things that you had mentioned, such as the duty cycle and voltage and environment. There are just so many factors, but the tunability, at least speaking from a gearhead, seems to be quite attractive. Okay, and it looks like we have time for maybe one more question. Um, the question reads, can the high voltage electronics in this system handle quench conditions that cause the spark to be suppressed due to either very low or very high pressure at the spark tip? Or do quench conditions need to be avoided?
Well, uh, eh, you know, it. I guess the first part of my answer is, to my mind, it's not that simple. Quench condition is an interactive condition. Um, you have to have enough pressure there to have a conductive path, number one. That is, there is no spark in the complete absence of gas. Well, if there's no fluid there, then there's nothing to spark into. There, you didn't open your valve, so what would be the point of having a spark?
Sure.
But the quench, to my mind, is really about how fast does the energy in a given spark, how fast is it dissipated, and does it go into promoting a combustion reaction, or is it swallowed up by some cold propellant, and thus the spark itself is quenched, but producing no combustion because the energy is transferred to cold fluid prior to mixing with the mating component, the fuel typically.
Hmm.
Most often you put the spark through the oxygen and have that spark swept into a zone where you've injected some fuel. And if you have the combination, the three things, the ox, the fuel, and the spark, you get ignition. So to the question of quenching, that's what was happening in the cold soak test, was we were not getting enough spark long enough for it to reach the mixture that could be lit. And so effectively that was a quench. Since then, the improvements we've made have helped the spark deliver more energy at the tip as opposed to being dissipated in the cables and connectors along the way. And so that was the improvement for us that we've now realized, that we've now demonstrated, I should say, is that whereas we used to be unable to light these thrusters at a cold soaked condition with cold propellants being fed into the thruster, in the test at Plumbrook, it would not light. We have now recreated those environmental conditions and achieved reliable ignition with this as our exciter assembly. So I think perhaps the answer to the question about quench is a lot of energy is lost in the transmission of the energy from the high voltage source to the spark plug tip. By eliminating that transmission distance and the intervening connections and resistances, we've been able to deliver the full spark energy that was generated in the coil all the way to the spark plug tip. And there's enough energy that it does persist, that it does not quench, and we do achieve ignition.
Roger that. Bill, thank you so much. And my apologies to those of you that are still submitting questions. We obviously, you had Your excellent presentation had generated lots of interest, and these specific questions are fantastic, but I wanted to make sure we let the audience know that please continue to submit them, and we will get back to you on those. And but I should say that unfortunately it is all the time we do have for today. And as I just mentioned, we will follow you up we will follow up on your questions that we didn't get to. We'll shoot for the next business week or so. But please feel free to email them to us at the address on the screen. So even after we end this webinar, so that we can get to those as well. But once again, we appreciate Bill your time, and it was a fascinating presentation. And the audience, thank you for taking time to be with us today at NASA Tech Transfer, especially as we bring this type of technology down to Earth. So I'm JC Hernandez. Have a great rest of your day.
Bye, everybody.